All right, well, if you're with me so far, give yourself a pat on the back. Great job. We're almost done. I think this will be the last video. I might break it up. We'll just see how I feel a little farther on. Not too much left. So last time we showed that if you take the collection of all open balls under a metric, that collection actually is a base for a topology. It generates a topology on your set. And so I want to give that a name. So here's our setup. We have a non-empty set, a metric on our set, and then we're going to call the topology generated by all the open balls the metric topology. And we're going to denote it by F. Instead of F, we'll say F sub D, where D is our metric. And so the pair X, comma FD. So here's your set. Here's your set of subsets. These are the open sets. This is called a metric space. And you've probably heard those words before, and now you know what they mean. So a couple of examples. The standard topology on R is indeed a metric topology. If you recall the standard topology, we said U is open if and only if for every X in U there exists an epsilon bigger than 0 such that the ball of radius epsilon around X is contained in U. That was our definition of the open sets. And this is the exact same topology that the metric d of xy equals to the absolute value of x minus y generates. So the standard topology all along, even though we didn't even know what a metric was, it is a metric topology. I wanted to look at another example with you. So let's think about a non-empty set. I'm actually going to scoot this up to save a little space. We're doing good. We're going to get done in this video, I think. So let's think about D, the discrete metric on a set X. All right, and so I know that there is a topology generated by this discrete metric, and the question is, what topology is it? Well, let's think about it. So given, we already worked this out actually, but given a point X in X, the ball of radius epsilon around X is either the set X itself when epsilon is less than or equal to 1, and it's the big set X whenever epsilon is bigger than 1. So this open ball of radius epsilon is the singleton set little x, or it's the full set X depending on your epsilon. And so the point that I want you to see, though, is this. Whatever this topology, when I take the collection of all open balls, I'm going to pick up every singleton set. So let's think how we want to say that. The metric topology is going to contain, we'll say contains all singleton sets. So the metric topology, let's say it like this, the discrete metric generates the metric topology, right? It generates the discrete topology. The discrete topology is where every possible subset of X is open. And we prove that anytime all the singleton sets show up as open sets, then you've got the discrete topology. Well, our metric topology, when you take the discrete metric and you look at the topology it generates, it's going to contain all the singleton sets. And so somehow the name makes more sense, right? The discrete metric actually generates the discrete topology. So I wanted to end this section with a short proof with you, and then I've actually got some homework all picked out for you. I don't think you'll find it too terrible. I've even got a hint lined up for one of the problems, so that's good. All right, so it turns out that a metric space is a Hausdorff space. Now, some of us have forgotten what a Hausdorff space is already, and that's fine. Pause the video, go back and remind yourself real quick. All right, here we go. So I want to show that any metric space is a Hausdorff space. And The idea is I need to show that there's that I could always find a little bit of space, quote unquote, between my points. So I'm going to go ahead and I'm going to say, look, let's let X and then F sub D be a metric space. All right, and then I should probably indicate with my metric D, metric D. And I'm going to choose distinct X and Y in X. So I'm picking two distinct points, X, Y, and X. And I'm going to go ahead and I'm going to let epsilon be 1/2 times the distance between X and Y. And by the way, I should point out that epsilon is bigger than 0. Let's put that period out. Oops. Let's put that period outside. Epsilon is bigger than 0 because the distance is always bigger than 0. Multiplying by half doesn't change. This product makes sense because the distance of 2 points is a real number, so I can actually multiply those in a meaningful way. You should always think about those things. All right, so then I claim that the ball of radius epsilon around X intersect the ball of radius epsilon around Y is empty. That's what we're trying to show, by the way. We're trying to show that anytime you have distinct points, there are disjoint neighborhoods of those points. That's what it means to be Hausdorff. So I'm claiming that's true, and if I can show this, I'm done, by the way, but I actually have to explain why that's true. I can't just say it's true and then move on. So then this is true, since otherwise, I'm going to slip kind of a proof by contradiction in here. If you did pick a point Z in this intersection, so if you did pick a point Z in the intersection of the ball of radius epsilon around X and the ball of radius epsilon around Y, then the distance between X and Y would be less than or equal to the distance between X and Z plus the distance between Z and Y. Why is that true? This is the definition of a metric, right? This is just a triangle inequality. This is always true for any metric. And now I'm going to say, wait a minute. I know that the distance between X and Z is at most epsilon because Z lives in this ball of radius epsilon around X. So this is less than epsilon, and the same goes for the other distance. It's less than epsilon. Epsilon plus epsilon is 2 epsilon. But what was epsilon? Epsilon was 1/2 this distance. So this is exactly the distance between X and Y. And now there's a real problem. This is, let's just say, which is a contradiction. And make sure that you see the contradiction, right? The contradiction is you can't have d of xy less than d of xy, at least the last time I checked. And so actually, we should finish this with a sentence so we can say, thus, our space X FD is indeed a Hausdorff space. And so that's the proof. You made it, guys. Good job. So the homework, I'll type it up on our homework sheet as well. I want you to do 1, 2, 5, 13, and 15. This is from section 2.7. I think, I'm not going to say when it's due because this video will change. You know, you might watch it a different day than I am, but I'll put the due date in the homework list on Teams. I did want to give you a hint for number 15. So I wanted you to start with this definition. Go back and read it and make sure that you're familiar with definition 2.5.10. I encourage you to try to prove 15 by contradiction, and I want you to pay very close attention to theorem 2.5.16, part number 4. That will be useful for you. So it looks like we're ending just in time because my batteries are running out. I will be in contact with you. Great job. Always feel free to email me if you have any questions. Haven't heard a ton from you guys, so I probably will try to touch base with you on Teams. Hope you're doing well.